Hi, Angela Rasmussen from the University of Utah Electrical and Computer Engineering Department. And again, we're going to go through a third problem example for RL circuits. So again, refer back to my video on how to solve the steps to solving this circuit. And this first step is going to be to redraw the circuit, leave out the element, leave out the switch. And so this is going to be at time t equals 0 minus. And that means that I look at the switch now, is it up or flat? And before the switch happens at 0, it goes up. So it's going to be down, and then it goes up at 0. So 0 minus is going to be flat. And then an inductor that sits for a long time is going to be it's going to be a short, so a wire here. And I again like node voltage, so I'm going to label this node Vx, and this is my ground. And then I see minus, 60 microamps is coming in, so I can just say minus 60 micro. And then this one is going to be Vx over 10K. And then this branch is going to be Vx over 10K. I also note that IL will be Vx over 10K. So now I can solve this for Vx. So I have 1 over 10K plus 1 over 10K is equal to 60 micro. And again, remember micro is 10 to the minus 6. Write that one. 10 to the minus 6 for micro. And see it. And then combining these, I get, I'm going to just combine them and multiply them. So 1 over 10K plus 1 over 10K is 2 over 10K. So I can do 10K divided by 2. And so that ends up being, let's see, 10.5 times 60 micro times 5K, whatever that is. And then IL is Vx over 10K, so 30 micro. So this will be my initial value because at 0 minus, IL at 0 minus equals IL at 0 plus. And remember that the 0 plus is where your initial value comes from. So if I was doing a variable within the circuit, I would use the 30 micro. I would redraw the circuit and redraw the current going the same way you solved it in the first place, which was down in this case. And so that would be 30 micro. And then I put the switch in the location right after it moves. So in this case, it opens up. And so this would be my circuit to find any other variable that I want. And then that would be the initial value for that variable. All right. So I'm going to go to now the final one. And in the final case, again, this becomes a wire. And then it is now opened, and so this will be an open here. So again, hopefully you can see that there's no source here. And so it's kind of like two resistors dangling and they're floating wires, so IL will be 0. But again, if you don't see that, that's okay. Go back, do Vx and do ground, and then do your equation of Vx over 10K plus Vx over 10K equals 0. And then you're going to see that this will be 1 over 5K. And so Vx has to equal 0, therefore IL will be 0. So mathematically, that would be the solution for that. Now we want to find tau. And in tau, redraw the circuit, element, leave out the element, leave out the switch. Determine the position of the switch, which in this case will be open, and put A to B where your element is, and then all the sources go to 0. So when this source goes to 0, it becomes an open. So my pathway is just going to be RTH is going to be the 10K plus 10K for 20K. And tau then is L over RTH. And we go back and look at L. And L is given as 3 millihenry. So we do 3 milli over 20K. And that ends up being 150 nanoseconds. And remember, nano is 10 to the minus 9. Now we can write the general form equation. So IL is going to be the final value, which is 0, plus the initial value, which was 30 micro, minus 0, e to minus t over 150 nanoseconds. And that will be amps. And then again, you can say for t greater than 0, or just put in a u of t times this equation. All right, thank you for watching.